Well, first of all, I would like to thank the organizers for giving me the opportunity of presenting my work in such a nice conference. And well, I am actually, since September, working back in the University of Granada, where I did my PhD in the Department of Statistical Mechanics. I have a classical background. Then I did a postdoc in Italy. And the last couple of years, I've been in Nottingham, working in the group of Juan Garrahan and Igor Lesanovsky. And the work that I will present here is precisely a work that I did with them and with another postdoctor, Federico Carollo. And, well, the results that I will present you are mainly contained in this paper that we published a couple of years ago. Well, the title is Fluctuating Hydrodynamics and Current Fluctuations in Boundary-Driven Open Quantum Chains. Okay, so with this talk, I'm going to try to connect ideas, techniques, methods, and tools from classical statistical mechanics to a quantum non-equilibrium system. In particular, I will try to apply these tools to the study of transport in boundary-driven one-dimensional systems. The sketch of the talk is as follows. I will introduce you the exclusion processes that Tomohiro has already spoken about them, in order to subsequently talk a bit about large deviations and macroscopic fluctuation theory. Then I will apply these classical tools to the boundary-driven open quantum chains, in which I will show you how we can derive for a certain family of open quantum system a fluctuating hydrodynamics in order to study current fluctuations. Finally, I will show you how we can make these rare events, these large deviations that are highly unlikely, how we can make them typical. So in order to control the statistics of a system on demand. Well, let's talk a bit about classical system, in particular classical diffusive systems, and think about one-dimensional system that we connect to two reservoirs at different densities. At the left, we have a reservoir with constant high density, and we connect it to the right reservoir, which is at low density. What happens then is that due to the difference of concentration in particles, a current is established, right? So if we measure the current, the cumulative current in time, due to this gradient, okay, we have a positive value up to a time t, all right? But what we are interested in is not the cumulative current, but the time average current. So we divide this value qt over the time t that we have evolved, run our experiment. If I do many realizations of this experiment, I can do the histogram of the current, and I get that, well, in this case, it's peaked around the mean value, okay? But if I do many, many times the same experiment, in some realization, I will get that the current flows from the low-density reservoir to the high-density one, so getting dynamical fluctuations. And this is what we call a rare event, and it's in the far tails of the distribution. So I am going to study this kind of events, the low probability of these rare events, and especially the structure that the system adopts in order to produce them. For instance, we can think that the stationary current is associated to a linear profile. That is what we have here in blue. Instead, a very low current is associated with another different profile from the stationary one, which is the one given by this red line. If we look at the trajectories of the system, and that will be a key in my study, the concept of trajectory, they will appear as this. For the stationary case, the linear profile is the average in time of these kind of trajectories. Here, I am representing in the x-axis space, the sites, here the time, and red dots are sites which are occupied by a particle, while white dots are empty sites. So if I average this kind of trajectory, I get the linear profile. While for a current much lower than the typical one, I have this kind of trajectory which are very different. Okay, in the long time limit and in the large size, we have that this probability in many cases is covered by the so-called last deviation principle, which is nothing but this exponential form that is telling us that the probability of observing a given current, a given time-integrated current Q away from the average decays exponentially with time and the system size. So they are very unlikely. And it's precisely this last deviation function, G of Q, the one which governs the probability, the whole statistics, all right, in the whole range of currents. So if we would restrict, for instance, to currents to small currents around the average, we could expand this large deviation function up to second order, we would have the central limit theorem result. But here, we are interested not in the small currents around the average, but in the whole current fluctuation regime. And this is the function that governs these statistics. And this plays a fundamental role in non-equilibrium systems because, as I will show you, it plays the role of an entropy density. So there are several methods to calculate this last deviation function, methods, microscopic methods and macroscopic one. I will start describing what we can do microscopically. So as Tomohiro already introduced us, here I am considering not the asymmetric, but the symmetric simple exclusion process. That is one of the paradigmatic processes to model diffusive systems. This consists of a one-dimensional lattice in which we have particles. These particles can hop to their nearest neighbor sites whenever these sites are empty. So, for instance, this jump cannot occur. And the jumps of particles to empty sites occur with a constant rate, p. At the boundaries, we will inject and extract particles with constant rates. And if these rates are different in one end and the other, we can drive the system out of equilibrium. And that is going to be one of our models of study. This is a continuous time Markov process that is described by the master equation, which tells me that the evolution in probability, the evolution of the probability of being in configuration C at time t is given by this expression, where W C prime C is the transition rate between from configuration C prime to configuration C, and RC is the escape rate from configuration C. This master equation can be written in an operator form, which means that we can write down the time evolution of a probability vector. This ket of P represents the probability, is a vector containing in each component the probability of each configuration at time t. Okay, so it has the dimensions of the number of configurations of our system. In this way, we can write this probability vector as the sum over PCT applied to C, where the set of gets C is an orthonormal configurational basis. So that we can write this master equation with this stochastic operator that is, in general, non-Hermitian. Well, and what we are interested in is in calculating the probability of some time-integrated observables depending on a trajectory that we call omega, that can be, for instance, the time-integrated currents, which are the net number of particles that leave the system, for instance, at the right end. We could also study other kind of time-integrated observables as the number of jumps in a trajectory, and that is what we call the activity. So the probability of having a certain value of this q up to time t is given by the sum over all trajectories weighted by its probability restricted to those trajectories that gives me the value of q that I am prescribing. Okay, and this form, this probability has a last deviation form, which depends in this way on the last deviation function. The same information, because sometimes it is not practical to work with this probability, it is better to work with the moment generating function, okay, which is the sum over trajectories of the probability of those trajectories e to the minus sq. And this follows again a last deviation principle with a different last deviation function, which is given by theta of s. So in this dynamical picture, the last deviation g and theta of s are two trajectories what entropy density and free energy density are two configurations in equilibrium statistical mechanics. One can go deeper in this parallelism, and we can see that here the time plays the role of a volume in statics. The order parameter is q, while s is the conjugate field. So the entropy density would be the last deviation function g of q, and theta would be the free energy, the dynamical free energy. And this is telling us that in this dynamical context, if we look at the singularities of this dynamical free energy, we will find how the trajectories of the system will change abruptly. We will find thus what we call dynamical phase transition by looking at the singularities of this dynamical free energy. But it involves the calculation of a partition function, of a dynamical partition function, which is this moment generating function. And this is in general not simple at all. But it can be shown that this theta of s is the largest eigenvalue of this deformed generator. This deformed generator is the original one in which we have multiplied the transition rates by e to the minus s alpha cc prime. And this alpha cc prime will depend on the observable we are looking at. If we are, for instance, looking at the current, this alpha cc prime will be +1 if in the transition from c to c prime I have jumped to the right, and it would be -1 if in the transition from c to c prime I have jumped to the left. While for the activity, this alpha would be always 1 because I am counting the number of jumps. So the largest eigenvalue of this guy will give me the theta of s. So I already have how to obtain the dynamical free energy from the microscopic dynamics. All right, but what can we say from the macroscopic point of view? From the macroscopic point of view, as Tomohiro has already pointed out, we can take the hydrodynamic limit of these models, and in the case of the simple symmetric exclusion process, we have a diffusive hydrodynamic equation by using the by rescaling the coordinates diffusively. All right, so the typical dynamics is diffusive. The dynamical exponent is set equal to 2, and we might be interested in asking, how about the fluctuations? Does the system adopt another kind of dynamics, another kind of critical dynamical exponents when conditioning it to have large current fluctuations? That is what we will study. And it is also remarkable, and is what I will show you now in the next slide, that from the macroscopic point of view, there is another approach that allows me to calculate the large deviation functions for classical diffusive systems. And in this case, this is the microscopic fluctuation theory. Okay, the main result of the microscopic fluctuation theory, which has been developed in the last 15, 20 years by 4 researchers from Rome and 1 from Brazil, is that if we start with a fluctuating hydrodynamics equation of this kind, okay, so by adding a noise to the deterministic current, this is a continuity equation describing the hydrodynamic of my system, which conserves one field, which is the density. So if I add a noise with this white Gaussian noise with 0 mean and covariance in this way, it's scaled with 1 over L and is proportional to the mobility of the system, that is related to the diffusivity through the Einstein relation, we have that the probability of a trajectory of having a density field and a current field is in the large size limit of this form, e to the minus L phi of rho and j. This rho and j is this quadratic form. So this probability is to trajectories what the Gibbs distribution is to configurations. So with this object, we can calculate whatever probability we want of observables which depend on this, on the density and on the current. In particular, we can calculate the probability of a time-integrated current. So if we do some calculations, we reach that the probability is given in this shape with a large deviation function, which that is this quadratic-like functional. Okay, so we have reduced our complicated problem of calculating large deviation from the microscopic dynamics to a quite simple one, which consists in a minimization of a functional which has as external parameters the diffusion and the mobility. This diffusion and this mobility is the only thing that changes from one model to another. So it's very, very powerful, very elegant, and by minimizing this functional, I find the optimal trajectory, meaning the optimal rho and j that sustain my system in order to produce a very rare current fluctuation Q. Okay, so this optimal trajectory can be thought as well as a sort of ground state for fluctuations, because in general, these ground states inherits the symmetries of this action functional. But there are some cases in which, for large Qs, this optimal path has not the same, is less symmetric than this quadratic functional. In this case, we have a dynamical phase transition of second order. So when we find an optimal path that is less symmetric than the action functional, and we can map one solution to the other, applying the symmetry that we are broken. So let's show an example of this. And for instance, we consider the weakly asymmetric exclusion process. That is very similar of the symmetric one, with the difference that now the rates are not the same of jumping to the right or to the left. Jumping to the right is enhanced by an external field, E, and this external field is divided by L, and this is why we call the system weakly asymmetric, because this E to the L is what is the reason why we have at the hydrodynamic level a field competing with the diffusion. If it was completely asymmetric, instead of having a diffusion equation, we would have a Vargas equation, as Tomohiro showed in the first lecture. So in this case, in the weakly asymmetric exclusion process, that now we are considering it with a periodic setting on a ring, we have, well, that the diffusive constant is 1. This is the mobility. And now we want to study current fluctuations. Okay, let's see how the typical trajectories associated to the typical currents, to the stationary currents, are. Typical dynamics gives trajectories of this kind. Here we have again sides, red dots are occupied sides, white is empty sides, and we have here that a current, well, is flowing because we are applying a field, but there is no structure at the density level. Okay, so we have a flat profile. However, if we condition the system to have very small currents, we see that what happens is that the particles stack together and start traveling with a constant velocity. So we see a clear difference from one regime to the other when conditioning the system to have very low currents. And this is reflected, as I have anticipated you, in the singularities of the last deviation function. And in this case, as we have a second order phase transition, these singularities means that the last deviation function is the second derivative of the last deviation function in some special points are discontinuous. Here we have represented the last deviation function. For typical currents, we have that it is 0 as expected, and if we condition to lower and lower currents, we have that below a certain point, below a critical current, we have this traveling wave phase, and here we have second order singularities of this function, and again for a range of small currents. Instead, if we condition the system to very large negative currents, we recover the flat profile phase. Okay, so this is telling us that what matters is the magnitude of the current around 0, not the sign. And it's a consequence also of the so-called Galois-Cohen fluctuation theorem. There are other dynamical phase transitions in one-dimensional system, as for instance in the Kipnis-Marchioro-Presutti model. And we have also showed this kind of transition in the two-dimensional weakly asymmetric exclusion process. Okay, we have seen that the microscopic fluctuation theory is very powerful when predicting large deviations. So, is it possible to derive a fluctuating hydrodynamic description? Is it possible to have a microscopic fluctuation theory for quantum spin chains? That's what we try to do, and you will see the answer in a few minutes. What I understand with open quantum systems is a system surrounded by an environment, and the whole system plus environment, has this kind of Hamiltonian, where H applies to the system that I am interested in, HM is the Hamiltonian that applies to the environment, and this is the interacting Hamiltonian. The whole system can be considered isolated, so it follows a unitary evolution, but as I have already told you, we are interested in the dynamics of this system. So by tracing out the environment, we reach to a mixed state that can be described in terms of a density matrix. Under some approximations that the environment are large, that the interaction is weak, that the correlation times of the environment are short, we can reach the known quantum master equation, which is given in this Lindblad form, that has two parts. One corresponds to the unitary part. This is the von Neumann equation. And the other one that describes the effect of the environment on the system through the jump operators. All right? This Lindbladian takes my initial state to a stationary state, and I will study all these fluctuations in these cases. There is a very nice analogy between this quantum master equation and the classical master equation I wrote at the beginning, and it was stopping a bit and analyzing these analogies, because if we understand these analogies, then bringing the tools of the classical StatMech to the quantum realm are easier. So we have that this is the more general form of a local equation in time, the Lindblad one, that preserves the property of the density matrix. And we have the classical master equation written in this form. So here I have written, and this is very well explained in a recent paper of Juan Garrahan in 2018, all this analogy. And we have this kind of dictionary between classical continuous time Markov processes and quantum continuous time quantum Markov processes. So in the classical case, we have this generator, W, that we already wrote. Now we have the Lindbladian. On the other hand, we have that the left eigenstate is the projection state, giving me a 0 eigenvalue, which is a statement of probability conservation. And in the case of the Lindblad equation, we have that the adjoint applied to the identity is 0. The right, the 0 right eigenstate is the stationary state in the case of classical stochastic processes, while in the case of open quantum system is the rho, the stationary state of the density matrix. Okay, and interestingly, we have that making the Hamiltonian equal to 0, calling the jump operators the square root of the transition rates, and making rho diagonal, putting in the density matrix the probability in the diagonal of the classical vector, we have that the master equation is equivalent to the quantum master equation. So this is telling me that we can write any classical stochastic process in an open quantum formalism. And once I have that, I can add coherent hopping and study the different regimes and see how coherencies, if we make this H different from 0, acts on the system. So for instance, we can write the classical simple symmetric exclusion process in this open quantum formalism in this way. We have now that the jump operators are given in the left end, are given by a rate which is gamma in times the creation operator in the first side. And the other quantum jump operator is gamma out times the annihilation operator. The same in the right boundary, and is what we have written here. And we can express our dynamics of the set. I was calling this previously P. I am calling it now phi. We can call this jump operator, which is creating in k plus 1, distracting in k, which is jumping to the right, okay, with this rate. And this is jumping to the left, creating in k and destroying in k plus 1. So with this, with my dictionary, I am able to write the Lindblad form of the simple symmetric exclusion process in this way. Okay, this is a shorter form of writing all this. Okay. Okay, so now the goal is, okay, what happens for if we include coherent hopping, and if in addition not only coherent hopping, but we include another kind of jump operator, say dephasing, which is given in this way. So now we have the SSEP plus coherent hopping plus dephasing, right? The coherent the dephasing term is written in the Lindblad form in this way, and the coherent hopping is we propose a tight binding model with this shape, with J being the coherent hopping rate. And depending on, we consider it for bosons or fermions, depending on the statistic of the creation and annihilation operator. So the question is, do we have a hydrodynamic in this case? what kind, do we have a fluctuating hydrodynamics? Can we do a macroscopic fluctuation theory description? How are the large deviations of my non-equilibrium steady states? Okay, as I want to derive a hydrodynamic equation, it's better to go to the Heisenberg picture, where I study the evolution of the observable, in particular the evolution of the occupation number. Okay, that is written in this way. Okay, so I can take the average, and I see that I get a continuity equation, right, with several contributions. So the right-hand side of this equation, I have a coherent contribution coming from the Hamiltonian, from the coherent hopping I was putting in my system, and a dissipative contribution, which is the one corresponding to the classical symmetric exclusion process. Okay, and I am going to take the hydrodynamic limit by scaling the coordinates in this way. So I divide the space by L times by L squared, and the macroscopic density profile is nothing but the mean, the average of the evolved occupation number up to this macroscopic time. And what we have is these hydrodynamic equations, where they are still diffusive, and with a diffusion constant that depends on the parameters of my system. This was previously studied by some of you. For instance, Victor Eisles in 2018 studied this case for gamma equal to 0. Also Snidarich in 2014, phi equals 0. And other cases, Teme and Wolf also. And if we have that make the dephasing equal to 0 and the incurrent hopping equal to 0, the diffusion constant diverge, and we have ballistic transport. So, okay, so far so good. The linear stationary profile, is linear and has this shape, and the stationary current is constant and has this shape with the D that I wrote down before. Okay, these kind of quantum chains are diffusive, but what about the fluctuations? How can we derive a macroscopic fluctuation theory-like picture? So we need the quantum stochastic trajectories that are obtained by adding to my previous Lindblad equation a quantum Wiener process in this way. Okay, in this case, we are just considering as a jump operator the dephasing one. So dB is an operator that acts on the environment and represents my quantum Wiener process that follows the Ito rule. Okay, by performing the hydrodynamic limit of this new equation, this is a kind of Langevin equation for a open quantum system, whose average gives me the Lindblad equation. And if I take the hydrodynamic limit of this, what I get is the fluctuating hydrodynamics that I got for the simple exclusion process. And in this case, for fermions, we have that the mobility, we have that the system behaves as the simple exclusion process, while for bosons, the system behaves as the simple inclusion process. This is reflected in a change in sign in the mobility. So we have 2 rho times 1 minus rho for fermions, 2 rho times 1 plus rho for bosons. And again, we have the same form of the for the noise, which is Gaussian distributed with this amplitude. Okay, so we got it. We can apply the MFT to these systems. Okay, so we can apply the macroscopic fluctuation theory to the large system size of fermionic or bosonic systems in this context. So okay, I'm going to compare both approaches, the one that I just derived from the fluctuating hydrodynamics, but I have still I have to tell you how we got the dynamical free energy from the microscopic dynamics in the case of quantum systems. Okay, so again, my observable of interest is the time-integrated current, the number of particles leaving the system through the last boundary, this is, and so the probability of having a current Q is nothing but the trace of the density matrix of Q, which is which we can get it restricted to the quantum stochastic trajectories having the prescribed current Q. This probability has a last deviation, follows a last deviation principle, and we again prefer to work with the moment generating function or the dynamical partition function. In this case, this theta of S for classical system was obtained by the largest eigenvalue of a deformed operator. In our case, it is obtained by the largest eigenvalue of tilted or deformed superoperator, okay? That is the one that I have written here. So we are multiplying by e to the s the last side, because we are measuring the current passing through the last side. So e to the s times the jump operator, the annihilation jump operator in the last side, plus e to the minus s, the creation in the last side. So for s equal to 0, we recover the usual dynamics, the stochastic dynamics, and for s different from 0, calculating the largest eigenvalue of this, we have the theta of s. So in this way, we can compare and verify the fluctuating hydrodynamic approach, comparing what we get from this microscopic computation and the predictions of the fluctuating hydrodynamics. And that is what we did by calculating the structure factor for different values of S, for different values of the current, conditioning the current to different values, which is what this S represents. And we had a very nice agreement. This is for L equal to 11 for fermions, and the solid lines are the fluctuating hydrodynamic predictions. So this is the structure factor, which is the Fourier transform of the density-density correlation function, and we have a very nice prediction. And in addition, we have that these trajectories are hyperuniform because they decay linearly with k for small k, all right? And by computing the dynamical structure factor through the fluctuating hydrodynamics, we got also that the system for S different from 0, it has a dynamical exponent equal to 1. So for currents away from the average, the best way of the system to carry them is ballistically. So in order to have a more physical picture of this, we performed some simulation for the simple symmetric exclusion process, that is to what our fermions tends in the large size limits of this kind of dynamics. So in equilibrium, okay, we have that for S equal to 0, which here I am not conditioning to have any current, we have this kind of trajectories. And the profile is 1/2 because I have this condition at the boundary. But as soon as I condition for S different from 0, I see that the average current, that the average profile is the same. The structure of the trajectories are clearly different. Here I have what we call a hyperuniform state, where particles and whole alternate more than at randomly. Okay, while if we just look at these density profiles, we wouldn't find any difference. But looking at the structure factor, we find the differences. The same happens for if we drive the system out of equilibrium. So we have different densities at the boundaries. The stationary state is linear, and by conditioning to have a very large current, we have a hyperuniform state. Okay, but this is occurring for so these are everything rare events, all right? And many of you could say, okay, why do you care of these rare events? They are very interesting, very nice, but they are highly unlikely. They say, okay, but if you find something interesting in the fluctuation, there is a way of bringing that fluctuation into typical. And that is what I will show you in the last part of the talk, how we can modify the dynamics, how we can find an effective dynamics that brings me this rare event into typical. So I am going to consider a different setting. We could do the same for currents, but in this case, I am going to consider a 3-qubit system coupled to a laser field. They are interacting and coupled to the environment. So we have a rate of photon emission which is equal to gamma, and omega is the Rabi frequency. So in this system, we can detect a long time the photons that my system emits. Okay, and this is a trajectory of the system. All right, this is the distribution of these counted photons. Okay, so we have a mean equal to Ka, but a rare event which is emitting many photons. Okay, that is what we represented in red. Okay, maybe for some reason I am interested in reproducing that rare event into typical. Okay, I want my system to emit more than typical, than how usually it does. So I want to reproduce this rare event in a normal trajectory. All right. So the question is, how do I have to modify the Hamiltonian and the jump operators in order to have a physical system reproducing this rare event? And say, okay, you have the deform operator. Okay, the deform operator gives you this kind of statistics. Okay, but the deform operator gives me this kind of statistics at a theoretical level. I cannot perform a physical system with this deform operator. Why? Because it is not physical. It doesn't conserve probability. Okay. This is the dynamics of a rare event, but it is not physical. So the goal is to transform this deform operator into a Lindblad form. And that is what we call, we will modify H and J into H tilde and J tilde, and we will end up with a Lindblad operator. Okay. And this, well, in this way, with this tilde, I will conserve probability. And we can show that this is what we call the quantum dupe transform, because dupe showed it for classical systems. And here we have this tilde superoperator, okay, without any deformation. But now the deformation, we have to transform the original H and J's in this form in order to bring this into this shape. So by calculating the dynamical free energy for a given S naught and the right and the left eigenmatrices, we are able to deform my system in this way in order to bring it to a stochastic superoperator. Okay, the transformation in classical system is done in this way. Okay, so in classical systems, I deform my operator. This is the deform operator, which is not stochastic. If I multiply by these matrices that are this L is a diagonal matrix containing the left eigenvector. All this is a stochastic generator, and that's the way of doing the dupe transformation in classical systems. So this allows to tune the system to any point of the dynamical phase diagram. So as I told you before, if I detect something interesting in the fluctuation, this is the way of transform my system into something physical. But sometimes it's a mess. So it is convenient to study the main components of this transform Hamiltonian on this transform jump operator in order to detect, in order to do some approximations. For instance, in this case, if we want to reproduce events corresponding to very large negative S, we see that the main contribution is given by these operators. And again, for the jump operators, we see that for large negative S, we can approximate them by these two jump operators. So in this case, we have a modified laser field, and it becomes non-interacting. So somehow this opens up the possibility of tailoring open quantum systems in order to obtain a desired statistics of emission on demand. And the same thing can be performed in this way for classical systems. Okay, that was basically what I wanted to tell you. So as a summary, we can say that I hope to have convinced you that large deviations are worth studying because they are the analog of the free energy in non-equilibrium systems in a dynamical sense, as we've shown before, that the non-analyticities in the large deviation functions, the singularities in this theta of S, are associated to dynamical phase transition, which are abrupt changes in the trajectories of the system, sustaining these large fluctuations, and that in the fermionic case, they feature a dynamical phase transition for atypical currents, and is associated with trajectories that are hyper-uniform and rare dynamical behavior that is ballistics. And finally, we have pointed out how these rare events can be made typical, and this can lead us to the construction of system with statistics that we can control on demand. I would like to thank my collaborators, Juan Garrahan, Igor Lesanowski, and Federico Carollo from Nottingham, and some of the results that I show regarding the classical case, the classical weakly asymmetric exclusion processes were done with my PhD advisor, Pablo Hurtado and Pedro Garrido, and that's it. Thank you very much for your attention.
Questions?
Just a naive question. So when you talk about construction of